This lecture is the second of 4 lectures for Chapter 1. It will cover sections 1.6 to 1.8 in the Chemistry and Context 7th edition text. The chapter is called The Air We Breathe. We're looking at the same questions for the entire chapter, kind of the composition of air, what are the molecules in air, how do we talk about molecules in the field of science, and then we'll eventually get to air pollution and understanding how the quality of air impacts us a little more. So this part is going to be some fundamentals, including an introduction to the periodic table, the classification of matter. Within that classification of matter, we'll be talking about the difference between mixtures and pure substances, atom versus molecules. We're also going to talk about how to name molecular compounds. So here we are, the periodic table, and it's quite overwhelming if this is the first time you've seen it. It looks like there's quite a bit of information. Each of these symbols represents the name of a different element. The numbers underneath it give information about the mass of that element, and you can see they're becoming more and more massive going down the periodic table. Then you have this strange floating group of elements here, and really they're inserted into this area of the periodic table. The reason why they're inserted below is just to show the periodic table in a reasonable amount of horizontal space. The periodic table is broken up into groups. Frequently, we refer to the elements on this side of the periodic table and focus in on the elements on this side of the periodic table. These are known as the main group elements, and they're the most common elements, or some of them are at least the most common elements. So often we talk about group 1, group 2, you see these little numbers above there, then group 3, 4, 5, and so on. There are also a different set of numbers above those, but we won't refer to those very much in this course. There are also what are called periods in the periodic table. This is considered period 1 going across, period 2 going across, period 3 going across, and so on. The atomic number provides information about how many protons there are in an atom, and we'll talk more about what a proton is later on. There are a few groups that you do want to know by name. Group 7 is known as the halogens. They're very important in environmental chemistry. In particular, there are the noble gases. You would have heard of some of these elements, such as neon in neon science. Those are the primary ones for now. We may refer back to some of the other important groups later on. Now, if you'd like to pause, there are a couple of videos or activities in the Chapter 1 Part 2 module. They are optional. I'm going to cover the same information in this lecture. But if you'd like additional reinforcement or the information presented in a different way, feel free to check those out. Let's first talk about the classification of matter. Matter can be categorized into different groups or classifications based on its properties. So one of the questions that is asked of a sample of matter is, can I separate the matter? Is there something I can do physically, such as, what I mean by physically is boiling, filtering, like you might filter coffee grounds. Can it be separated? If it can, then it's a mixture. Another example of that would be maybe iron filings in a sample of sand. If you were to run a magnet over the sand, you could separate out the iron filings using physical means. If you can't separate out the substances from one another using a physical process, then it's a pure substance. To further categorize the type of matter, if you know it's a pure substance, it can be one of two different groups. It could either be an element or a compound. If it could be broken down further into even simpler components, essentially what we're getting at is if it's a compound, can we actually break up that compound into elements? For example, sodium chloride is a compound. It cannot be separated by any physical means. That's why we're down this portion of the tree. But you can separate sodium chloride using chemical means into the individual elements. Once you have something that can be no longer subdivided, you have essentially an element. We refer to element as the fundamental form of matter. The elements themselves are all made up of atoms with different properties, but we'll get to that later on. So as an example of using that classifying tree, let's look at these different substances. We have carbon dioxide, nickel, perfume, and propane. The first example, carbon dioxide, can we separate that molecule using physical means? No, we cannot. So therefore, it must be a pure substance. Could we use chemical means to break it up into its component elements, carbon and oxygen? Yes, so it's a compound. Assuming you have a sample of pure nickel, not like a nickel coin, but pure nickel, that, if you look on the periodic table, is in fact an element. So once you have a pure element, that cannot be broken down any further, and so its identity. If you've ever looked on perfume is a mixture. If you ever find yourself with a bottle of perfume and look at the ingredients, there are various fragrances added as well as usually an alcohol solution of sorts. Since it's a number of different compounds, it's a mixture. Sometimes it may be difficult to identify if you have a mixture, if you're uncertain of what the mixture or what the example consists of. A good rule of thumb is that if it looks like a chemical name, it's either a compound or an element. If it's something in day-to-day life, the majority of foods or beverages or things we use are mixtures. Propane perhaps is an exception to that. Propane in our propane tank in our barbecues, that is a compound. That's a pure substance. It's possible that there may be some oxygen mixed in, but if you see just propane itself, that's a chemical name, you would assume it's a pure compound. So thinker buddy question. A substance that cannot be broken down into simpler substances by chemical or physical means is a compound, an element, a mixture, or a solution. It is an element, so if it cannot be broken down any further, it's an element, one of our fundamental building blocks. Now go ahead and pause the video and see if you can identify these as an element, a compound, or mixture. Fluorine, once you become more familiar with the periodic table, you'll know that that's just an element. Table salt I talked about earlier. It's composed of sodium and chlorine. It's a compound. Soap, again, things around you in day-to-day life are more likely than not mixtures. Soap is clearly not a chemical name of any type, so it's not going to be an element or a pure compound. Seawater, you know there's salt in, there's water in, so it must be some type of mixture. So let's take a moment to just review what we learned. Elements are made of individual atoms. They cannot be broken down into simpler substances. One caveat to that is particle physics, but we're not going to discuss that. For now, just as terms of chemistry, we're calling elements the simpler or the simplest substance. And they're all listed on the periodic table. And it's elements that compose all matter. Now let's talk about compounds. Two or more elements bonded together is a compound, and we were looking at that earlier. They have properties different from the original elements. If you look at sodium, it's a very reactive metal. It reacts very explosively with water. And chlorine gas is a poisonous toxic gas used during World War I as chemical warfare agent. But of course, when you combine the two together, you have sodium chloride, a mineral that is essential to our well-being. So here we have an example of water molecule. This is called a space-filling model. The red blob here represents the oxygen atom, and these white spheres represent hydrogen atoms. So there are a few ways to represent compounds. We've seen a few formulas. This is the formula for ethanol, the active ingredient in beer, wine, and spirits. It's what intoxicates people or animals. This is two different ways to write it. Sometimes the molecular formula is written out in a way to give information about how the atoms are connected, but you don't always see it written out in such a fashion. If you can see here in the structural formula where we write out very clearly how the atoms are bonded to one another, you can see that the two carbons and the hydrogens are in fact on one side of the molecule, and this OH is on the other. That information isn't provided in this version of the molecular formula. There are two other types of representations we'll see. One's a ball and stick, and it just uses spheres and lines to indicate how the atoms are connected. So these would be carbon atoms. These would be hydrogen atoms. Hydrogens are generally white in model kits, and carbon atoms are generally black or dark gray. Oxygen atoms are generally red. Then we have the space-filling model for ethanol, similar to the space-filling model you saw previously for water. And it's perhaps a little more accurate in a sense because atoms are really these spherical clouds of electrons on the outside with a nucleus in the middle. In order to understand the concepts in chemistry, we want students to be able to visualize chemistry on the atomic level or the particle level, to actually know what is going on at the level of atoms. So if you can visualize that, you're more likely to retain the information and understand the information. So here are just some particle representations. Here's maybe argon gas in a container. Argon is one of the noble gases. Then here are some molecules of an element. Nitrogen bonded to itself in nitrogen gas. Then here we have a molecule with two different elements, carbon monoxide, a deadly gas that we'll talk more about, and we've talked a bit about already. And then here we have a mixture of an element, perhaps argon gas, and a molecule, carbon monoxide. So at times we may look at these particle representations to get a better feel for what is going on in the world around us, conceptually, at the particle or atomic level. Now you saw nitrogen earlier as a molecule, and certain elements in nature always are bonded to themselves, or are what is called diatomic. These, in our day-to-day life, at room temperature, are gases. And so they're diatomic gases. If you see hydrogen or oxygen or nitrogen or chlorine gas, you have to picture in your mind, okay, that's H2. That's two hydrogens bonded together, or that's O2. If we talk about oxygen in the environment, oxygen gas, that is O2. Oxygen does not exist on its own in our surrounding environment. It's always bonded to another oxygen atom. Now, in order to communicate to one another about chemical compounds, we need to have a systematic way of naming them. Otherwise, we're always going to be spitting out long strings of elements like, oh, are you talking about that C2H5OH molecule? What we really want to do is refer to it as ethanol. So let's look at the systematic name for molecules. A molecular compound, again, is two or more nonmetals. We'll talk about ionic compounds more later on in the naming of ionic compounds, which again consist of a metal and that says non-mental, but it should say non-metal. And we'll also talk about the naming of simple hydrocarbons, or organic molecules that we see a lot in our day-to-day life. So here's another picture of the periodic table. Again, period, group. The first rule is the element with the lower group number is written first. The element with the lower group number. So if you have something in group 4 and something in group 5, two elements, the element in group 4 will be written first. So let's look at carbon dioxide. You can see here carbon is in group 4, oxygen is in group 6. And so the carbon is written first. Rule 2, if both elements are in the same group, the element with the higher period number is written first. Now remember, it goes period 1, 2, 3, 4, 5, so we mean a lower period going top to bottom. We mean a lower period going top to bottom, and therefore a higher number. So SO2, sulfur is lower down with a higher period, period 3. So that is written before oxygen, which is in period 2. Rule 3, the second element is named as if it were an anion. And we'll talk more about anions and cations when we talk about ionic compounds. But the key here is that the second element will have a change in the stem of its name. So oxygen becomes oxide. We add the suffix "ide" to the name of the element. SO2, sulfur dioxide. And the di refers to the number of oxygen, which brings us to Rule 4. We use Greek prefixes to indicate the number of atoms. So let's take a look at those down here. There's one exception. If the compound contains only one atom and it's the first element in the molecule, you don't use the mono prefix. Okay? So an example of that is carbon monoxide. You don't say monocarbon monoxide. If it's the first element and there's only one of them, we don't use mono. But here we have di, meaning 2, tri, meaning 3, tetra, meaning 4, and so on. So you should memorize these, or definitely if you're taking note cards during the lecture, this is a point where you'd probably want to pause and make some note cards, or definitely jot this information down. Rule 5, if you have a pure substance in its elemental form, you do not state the number of atoms. What does that mean? Well, argon, okay, it's only one atom, so that's easy. It's just argon. But nitrogen, remember, like I said earlier, nitrogen is just named nitrogen gas. It's not dinitrogen. So nitrogen is, the N2 is only composed of nitrogen, so we don't say dinitrogen. Same thing with chlorine. Chlorine gas, not dichlorine. So let's do some examples here. We've got, let me make sure I get a good color. We've got dioxygen fluoride. The di tells us there's 2. Okay, and the fluoride, this is really just fluorine with that stem change. All right, carbon, that's easy enough. Trisulfide. This "ide" was added to sulfur. So that's carbon, and the tri means that there are 3 sulfurs. Pentanitrogen hexabromide. Penta, you'll have to memorize that, means 5. Hexa, that means 6. So we have nitrogen, and we have bromine, and so we're going to put 5 nitrogens and 6 bromines. Now these compounds may or may not exist. This is just an example using the naming rules. Let's determine the name. I've included these nifty boxes so you don't have to suffer through my handwriting. So we've got sulfur and we've got chlorine, but we've got 2 chlorine atoms. So di, chlor, and then we're changing the chlorine stem to ide. Okay, carbon, and we've got 3 oxygen atoms, trioxide. The P represents phosphorus, diphosphorus, and then we've got 8 oxygen atoms. 8 is an easy one to remember, 8 like the octopus. Octa, oxide, which looks weird, but is correct. Now you should give it a try and do a little practice. Try to create the chemical formula from these names here, and then convert the formula to name down here. And these are the answers. If you have a question on any of them, feel free to post on discussion board or email your instructor. One of the last topics for this portion of Chapter 1 is naming simple hydrocarbons. The reason why we want to talk about this, of course, is our issue of fossil fuels today. We use hydrocarbons obtained for fossil fuels in many, many different applications. Hydrocarbons by nature are composed of carbon and hydrogen primarily. Methane is one of them, methane used to heat your home. These use a slightly different naming system since they are what is known as organic molecules composed of carbon. We are going to learn a few of the prefixes for now. Meth is a prefix for hydrocarbons with one carbon. Really, if we're only talking about hydrocarbons, that's methane. Eth, if the hydrocarbon has two carbons, it has an eth prefix. And 3 carbons would be prop. 4 carbons would have the prefix bute. So to put it into context, propane is a organic hydrocarbon used in our barbecues, and it would have 3 carbons. The prop tells it it has 3 carbons, and it looks something like this. So here we have a portobello mushroom grilling. Looks like it actually might be charcoal, but you get the idea. And then there's cheese there. Cheese. I shouldn't record these when I'm hungry, but moving on. That ends Chapter 1, Part 2. Might want to take a break, let that info marinate, or you might want to read through the text to fill in any gaps or reinforce the material.